Hello everyone, I'm Yujing, and together with my teammate Yu-Hsuan, we are excited to present our capstone project, Mammal2Metal, 4D reconstruction from monocular videos. This work is conducted under the guidance of Dr. Genchan Yang, John Zhang, Professor Z, and Professor Deva Ramanan. In this day and age, robotics shows tremendous potential to boost productivity and to take on hazardous tasks that would otherwise endanger human lives. From automating repetitive tasks to navigating disaster zones, robots can take on jobs that are either too dangerous or too labor-intensive for humans, ultimately boosting productivity and protecting lives. But compared to computer vision and language, robot learning still has a long way to go. While other AI fields have rapidly grown in capabilities, similar gains hasn't been observed in robotics. This gap stems from three key challenges that we have identified. Firstly, there's the sparse rewards in reinforcement learning. Secondly, there's limited robot learning datasets available. And lastly, there's a fundamental embodiment gap. To begin, robot learning in robotics often relies on sparse rewards. Success is only observed after long and complex trajectories. This makes feedback delayed and training both slow and inefficient. To make learning feasible, intermediate rewards are usually carefully designed. However, this tends to add significant engineering overhead. Secondly, robot learning datasets are relatively small and are often expensive to collect. This stands in stark contrast to the vast amount of internet data available for vision and language models. For instance, RoboNet, the largest available robotics dataset, is roughly 1,000 times smaller than How-To 100M, a vision language dataset scraped from YouTube. Lastly, an embodiment gap persists between biological creatures and these robots. Even when the robots are inspired by real creatures, their mechanical constraints makes direct imitation from these creatures a major challenge. In this illustration, we show the red key points on the robot's joints and green key points on the SMPL human body model. However, as you can see, there's a gap between the red and green key points. So, what can we do instead? While robotics datasets are limited, the internet offers an enormous pool of monocular videos and images, showing humans and animals performing a wide range of behaviors. Recent developments in generative models have also shown great potential to generate high-quality images as well. Thus, our project aims to perform 4D reconstruction in order to leverage the large-scale internet data available. This will allow us to overcome the scarcity of robot learning datasets. With 4D reconstruction, we can supplement the limited available robot learning data by tapping onto the widely available vision datasets on the internet. We can also bridge the embodiment gap by retargeting motion using customized rigs that matches the robot's physical structure. Imitation learning can also be used instead of complex reward engineering using the dense motion cues generated at Reconstruction. Equipped with these insights, Yu-Hsuan will now present our proposed approach to solve these challenges.
For the remaining slides, I will introduce our proposed methods in detail and explain how each component contributes to the overall system. Our pipeline includes data generation, post-mill regression, 3D skeleton fitting, and testing. The first part is about generating diverse images. To generate diverse robot images, we want the robot to have different poses. Since our automatic goal is to apply this method to a real robot, we assume that the robot typically comes with a mesh model, which can be used in a simulation environment. We utilize reinforcement learning to control the robot's movements in Monocular and render images of the robots using a virtual camera inside the simulator. At the same time, we use NVDFS to rasterize the mesh and generate the corresponding point maps. Besides pose variation, we also want our model to handle different types of images based on a given robot mesh. To achieve this, we use a large language model to generate diverse prompts following the template. Someone wearing a something. For example, the language model might generate descriptions like a man wearing a suit or a student wearing sports clothes. We then use generating models to convert these prompts into images. To maintain the same pose as the input robot, we provide depth and pose images as reference to control net. After obtaining the data, the next step is to train our main model, the point map network. A point map is an image where each pixel is associated with the XYZ coordinates of a 3D point. As shown in this animation, using only a single point map makes it impossible to fully reconstruct the entire object. To address this limitation, we predict multiple layers of point maps. Additionally, our network generates two types of point maps, a canonical point map and a pose point map. A canonical point map refers to the neutral pose. For example, for the human, this will be a standing pose. In contrast, a pose point map represents the actual pose version. We will illustrate why these two types of point maps are necessary later. After obtaining the prediction results, we apply a reconstruction loss, which compares the predicted point maps with the ground truth to guide the model toward producing more accurate and reliable outputs. The next part is about 3D skeleton fitting. As mentioned earlier, we predict both a canonical point map and a pose point map. By subtracting the pose point map from a canonical point map, we obtain the deformation field. This deformation field allows us to generate a post-rigid model. Here, I would like to highlight that instead of predicting the 3D model of the object, we focus on predicting in the robot's shape space. This helps reduce the gap between extracting motion and applying it to real robots. The final part of our pipeline is inference, where the input can be any video that captures the person performing various actions or movements. Our method processes this video to extract the underlying motion patterns and then transfers these motions onto humanoid robots, enabling them to replicate the observed behaviors in a realistic manner. That concludes our presentation. Thank you for listening.